All right, good afternoon, everyone, and welcome to the June chapter meeting for the Performance Virtual chapter. Appreciate you joining us today. Just a little bit about the group. I am both the moderator and the president of the group. My name is Ryan Adams. You can follow me on Twitter. I am at Ryan J. Adams on Twitter. We also have an account out there on Twitter for the virtual chapter itself, which is SQLpass_PVC. If you want to have a discussion and talk about today's presentation or have any questions or anything like that, feel free to use the PassPVC hashtag. And of course, we have our website, and we've got a couple of Google group lists that we use. So that perfvc at googlegroups.com is an open Google group list that you can use. You can join that. And what we do there is not only do we send out meeting announcements to that list, but we use that as a technical list too, right? So if you're having a performance-related problem, maybe it's a query that's perplexing you, or you've got a weight type that showed up or something you're not unsure of, shoot an email out to that list, and you will probably get an answer. So that's an open free resource for you. There's a lot of great, really smart folks on that list that can definitely help out and answer any questions you have. So take advantage of that resource. And if you want to reach any of us here at the chapter, of course, you can always email performance@sqlpass.org. For any technical assistance today, we are using GoToWebinar. You will notice there's a panel up in the right-hand corner. Now the panel will slide over to your side. If you want to expand it, you can click the little red arrow that's there at the top in order to see all of your options. You'll see a little raise a hand icon. If you're having some issues, we'll do our best to help you with that. If you click the raise hand button, we'll message you. If you are wanting to increase the size of your window, at the very top of the window, you should see a maximize, minimize button or a zoom button so that you can change that as well. As we're going through the presentation today, if you have any questions, there is a question pane. Feel free to type your question down there. We will answer some of those as we go, but we'll save most of those toward the end. And we'll try our best to get those answered for you. If we do run out of time, we'll at least have your question captured. I can send those off to Lewis, and I'm sure he'd be happy to maybe blog about them or something like that and get those questions answered for you. And also as a reminder, audio is only available through the computer system today. It's all VoIP here, so there is no dial-in number. We want to make sure we thank our sponsor, SolarWinds. Thanks to SolarWinds in sponsoring our chapter. They are our only sponsor that they take care of us all year long, that are able to bring these things to you every single month for free at no cost to you. In addition to that, allows us to give away a $100 Amazon card every month. So we will notify the winner within a day or two after the meeting, which will be chosen from random out of everybody that has attended today. So we want to make sure we thank SolarWinds for that as well. Next thing we want to make sure you're aware of is the upcoming PASS Summit. So if you haven't been, this is an amazing conference with just the best technical stuff that you can get. And the one thing I always like to point out about the difference between this conference and any of the other conferences you go to is almost all of the other conferences, the speakers are getting paid. Nobody gets paid at the PASS Summit. Your regular session speakers are not getting paid. They're there because they do this every single day just like you do. They do this because they love the community and they want to teach others and share their knowledge. And that gives this the best technical stuff that you could ever get compared to any of the others. So definitely keep that in mind. There's some great stuff out there on the PASS Summit website if you're trying to convince your boss to be able to go. There's a great write-up out there that you can actually use yourself in order to help justify that in order to be able to go. I do want you to be aware that you'll notice that the current price is $1,795 currently. There are price bumps, so the closer we get to the summit, the more the cost goes up. The next price bump is July 12th, so that's only a few weeks away. Now, if you use the code there, the big red arrow pointing to the code, if you forget that or are not unable to write that down, we have it on our website. So if you hit performance.sqlpass.org, it's right there on the right-hand side of our website, so you can go find that code anytime you need it. It will save you $150 off whatever the current price is. So today it'd be $17.95 minus $150 off of that. Obviously, July 12th, the price goes up. You could take $150 off of that price as well. So make sure you take advantage of using that code and get that $150 discount. Now, the next thing I'm really excited to announce is every year, for those of you that have been following the performance chapter here on a regular basis, we have what we have an annual thing we call the Performance Palooza. So for this year, it will actually be in place of our meeting next month. It'll be held on July 23rd. Running from, well, I wrote 9 a.m. to 5 p.m. Central. I'm sorry, it should have actually been 10 a.m. to 5 p.m. Central Time. And all the times are listed there. We've got some fantastic speakers, as you can see here on the screen. Some of these folks have spoken for us before, and we've invited them back because they've done just an awesome job. I know most of these guys personally. There's some really good stuff in here. John Starrett is always a favorite. Neil Hambly's a great one. Tim Mitchell is just amazing if you've ever seen him speak as well. I'm kind of strong-arming him into that 3 p.m. slot there. Tracy Jordan works for Microsoft, and he is on the Always On support team. And although he hasn't spoken a whole lot, he's done a lot for the user group and locally and some of the SQL Saturdays, but he hasn't spoken online a whole lot. This is an amazing chance to get to see him speak, and he's really, really good, where he will break it down and actually show us exact calls from customers and stuff. So it's one you don't want to miss. And if you're looking for some PowerShell stuff, Mike Fowles is amazing on that stuff. So take advantage of this. These are free. We haven't posted on the website. We'll get them up there very, very soon. We wanted to wait until after today's meeting to get those posted, but we'll get all that with the links to register on the homepage of our website here, probably within the next week or so. That way you can register for all these sessions. That's 8 hours of back-to-back amazing content. So make sure you check off your calendar, put a dummy thing in your calendar that says, boss, I'm busy for this time. Take advantage of this. It's a great training for you and completely free to you. With that, for today's presentation, Lewis Davidson is going to talk to us. He's going to talk to us about, used to be called Hekaton, but the in-memory database objects and how they can affect database design. So with that, I'm going to let Lewis introduce himself, and I'm going to change the presenter over to you.
Heck, I thought you were doing just fine. You could just keep going if you wanted to. I was learning some good stuff there. Okay, so today, in the next 53 minutes apparently, I'm going to talk about in-memory. I'm going to talk a little bit about the internals, a little bit about how it affects your design, what goes into building this stuff. So we're going to talk a little bit, and this is my corny joke of the day, a bit of RAM and disk. And I can't hear you laughing, but I know you are. So it comforts me to know that. All right, so who am I? I've been doing this for a long, long time. I'm a corporate data architect. I've been working for the same company for a very long time. And what that means is I've got the breadth of technologies versus the breadth of concepts. Like I've never worked in healthcare, I've never worked in banking, but it's all, tech. I'm very deep into the technology. I've done ETL, I've done database design, dimensional design, all sorts of stuff. I've written 5 books on database design. They were all the same book with slightly different titles. We're going to have a new one that's going to get rid of the version in the upcoming year and add all this stuff that up to 2016, which is going to be some really cool stuff. I love database design, and I like where this is taking us. This is in-memory technology, but it's a very different sort of thing. So we're going to talk about why it's different and how it matters to you. Just really quick, I'm going to give you 10 seconds if you want to get the slides and you can't say the whole time. They're going to be there. A couple of blogs. You can grab your snippet and grab that if you want to. It'll be out at the end of the session as well. If you look up drsql.org, you can't miss me. So I have only one request, and that is if you have questions, limit them to ones I know the answer to. So that's twofold. One, it's trying to be funny again. This is my not corny joke as last. I'm saying I don't know what's exactly going to happen in the new version. I don't know exactly what's happening. I know what I've read. So I know a bit about, if you've read up about in-memory in 2016, you probably know as much as I do. So this is, I don't know how many people here are vegetarians. If you are, I feel bad for this slide. But if you're not a vegetarian, you probably like bacon. And bacon is the greatest food ever. It tastes fantastic. If you need to gain weight, which I do not, but it's a wonderful tool. It'll make you gain weight faster than you can imagine. but it's not good for everything. For example, don't try baking toothpaste. Don't try baking gum. These are really, really bad. So this tool is not going to be good for everything, but where it fits the scenario you have, it's going to be amazing. Okay. Originally, I built this for 2014, and all the slides still, the content are 2014 enabled. 2016 is really going to improve the feature set. I have bullets on the things that I've heard are coming that have been published, particularly by Aaron Bertrand, who I very much trust from his blog on what he learned at Ignite. And I'm going to note this for you so you know what's coming. Because the first version of this was more everybody in the room as I presented this would say, this sounds really cool. And then by the end of it, I might have one person who thought they possibly could use it. That's going to change, and it's tremendous differences that we have to understand. So when I came up with this idea, I wanted to figure out how to use in-memory. I said, let's build something, because that's probably the best way to learn. And I said, what about a sales system? And somebody's going to be inserting customer and order data just in a very fast stream. And how might that look, and how can we adapt that to using in-memory? And just to keep it extremely simple. And then learn a lot. Kaylin Delaney had a pre-con on this that was fantastic. She has a book that's fantastic. I have a list of papers that are interesting to read later on in the presentation. And then build a test. See what you can learn from it. Apply something in your real job if it's possible. And it's going to be possible in the future, because I know we have lots of places where there's contention. There's too much traffic trying to go into the SQL Server in certain places, not in our entire system, but only certain kinds of things. So what is it? It's a totally revamped engine that sits inside of SQL Server alongside the old engine, and it changes how things work. It was purpose-built for certain scenarios. A lot of the big companies don't use foreign keys. They don't use check constraints. They only have tables, and they treat this thing as a data storage device. Well, in those kind of scenarios, understanding some of the concurrency difficulties we'll talk about, you could just plug this in. But most people don't build like that. Most people don't cover all those cases for many different engines. So you may have to rebuild your entire application to fit this. The terminology to me is interesting, because our current tables, which we're going to call on disk from now on, whenever you access them, right, you access them from RAM. Ideally, everything, if you have all your data cached in memory, it's very similar to in one aspect to how in memory is. In memory, the home is in memory, but it's going to be backed up to the disk because you need to have durability. Your existing tables are on disk, but ideally they're all cached in memory. So that, this is not a replacement for DBC pin table. Okay, you're not just pinning it to memory. We're changing the architecture altogether. So this is going to make it very easy to use and very difficult to use at the same time. And that, to me, is one of the places where you get in the most trouble, because sometimes people get the idea that because it's easy, it's really easy. It's easy to drive a car, but then when you want to drive a car 10 miles an hour, it's a lot easier than driving it 1,000 miles an hour, because you run into mountains and things very quickly. Okay, so in the title I put database design, and I'm a data architect, and I architect stuff for both the early and the implementation. So you have to start out somewhere. So design, we do it before coding. Some people do it while they're coding, and then they find out that they should have done it before they coded and actually have some idea of where they're headed. Well, these coding patterns are going to change our design. And in this case, the way the engine works is going to change how you think about implementing your SQL Server database to get the maximum throughput and the maximum data integrity. So we have this natural process. The waterfall process was the old-timey, you gather requirements for 600 years, you design for 600 years, and then you go back and start again because technology's changed and the developers already built something anyways. So we need to do it in smaller iterations, but it's still something you have to do. So let's talk about how in-memory might change our design development lifecycle. So we start out with a conceptual logical model. We want to get the data requirements for a data model, know what we need. Then the next step is this, how are you going to implement this? Well, you know, if I have 100 transactions a day, well, I probably don't need to use the most expensive tool. I can use SQL Server Express maybe, I can use Access or Excel or even paper. There are organizations out there that would be much better if they just used paper. But we're going to assume here that we're talking about a need that's really highly transactional. I need to make sure that it's not like NoSQL, where you have, you know, eventual consistency. We want to have consistency immediately, but we want to have it very quickly. Then we have engine choices. Do we want to use the in-memory engine? Do we want to use the on-disk engine? Do we want to use compression? Because that'll give you more performance, as you probably know. You know, do we want to use partitioning? And that can sometimes afford some level of performance value, not generally a performance feature most of the time. And a lot of these bad choices are because some guy with pointy hair comes in your office, says, you know, in-memory is great, use that. Like, okay, you know, because you can't fight the pointy hair guy, because you can't fight insane, right? And then you have to build something. So you have this physical design, you write your relational code. So we're going to talk about how each one of these phases might be affected. We're going to spend a lot more time on the internal kind of physical design, so don't think I'm going to keep talking about just nothing that you care about if all you want to know is the internals, and because that's really the biggest part. Because let's be honest, your design should not change. You still need to know what the user wants, what are the attributes of every kind of entity they want, what makes each row unique, and what are the predicates that surround your table, your data. And these choices are going to make it easier or more difficult to use the engine with its limitations now and its limitations later. So nothing changes in that particular case. So for my design here, I have a customer table, and they have addresses. And they're going to have sales orders and sales order items. I have a product and sold at a price, so we're going to sell a certain number of items to a customer. I'm pointing at the wrong screen, but you can see you can see the things, right? So this was my base design, and we're going to add to this. We're going to use this when I do the physical design. I have code that's downloadable from my website, which implements this and gives you the testing data and everything you need to try it out as well. I don't have time to do that and kind of introduce the topic, the engine too as well. So we're looking at the physical implementation. So we want to know how this thing works. Well, currently you have this, your client app talks to SQL Server through a TDS stack, right? You send it some SQL, it goes down, it gets a cache, it parses it, algebrais, it sends it back, optimizes it, sends it back, and you have interpreted code. So every SQL statement is run one step at a time. And if you look at the plan of a query, you'll see there's these operators, and those operators are in there, and it's interpreted language. It changes at runtime. So then we're going to access the data. So when we say we need some data from SQL Server, we go down to the buffer pool. If it's in the buffer pool, we don't need to go to disk. This is why I'm saying very similar to in-memory. So we go down, we grab it. If it doesn't happen to be in memory, you know, it goes down to the data file group, reads the data, brings it back in, and all this code works just like the data was in memory to start with. You just had this latency for getting the data. When you make changes, you write to the transaction log. Well, now we have these new hackathon components. I took this slide exactly and basically just formatted the color, so it's listed as hackathon. So we have this compiler now, which compiles your code down into machine language. So we have these natively compiled stored procedures. I'll give examples of the code a little bit later. But now if you write a stored procedure and it's compiled, you go right into the engine. It uses the memory optimized tables in a native manner, all compiled DLLs, and goes right to the tables. You know, it does all its work here. So when you have a checkpoint, you're going to then write the data to these memory optimized table file group, which is called Delta files. And so you can persist your data over time. Your server crashes, you still need to be able to get back to this data. You can also access these tables through what's called Interop mode, and we'll talk more about this in more detail later. But So you come down into here, it runs a query. It says, oh, this is a memory optimized table. It goes and runs and brings it back, and you can join those two tables together from both sides of the picture. You'll notice this, the natively compiled stuff can only use the natively built tables. So all this is in RAM, all this is in DLLs, and you can actually get down, if you go to a different session, look at Kaylin Delaney's stuff, you can actually see these DLLs and see the code that gets created. What you're going to look at is a really tremendous benefit if you can put everything in natively compiled code. You're going to see 2 to 30 times improvement based on the overhead you have to deal with. So there's still overhead here, there's still overhead in writing and transaction logs. So depending on what you can do to make it better or worse. So we also have a lower use of the transaction log because you don't persist indexes for starters. So we have our table, we only write data from the table into the memory optimized file group. Here we write only table changes so we can do rollbacks. Well, not so we can do rollbacks, but so we can do restores. Here we have, so the indexes are built here, and we'll talk about the structures, they're much different as well. But if you have to restart the server, it rebuilds the indexes from the data after it loads the data back into the tables. So your time to restart a server might be a little bit higher, but it certainly is much helpful while it's running. I have not seen SQL Server crash myself in a good amount of time. I've seen some servers hang up, but generally not seemingly from SQL Server. I won't get into the reasons. Checkpoints are still background sequential I/O, just like they are over here. You have dirty data in your tables, memory structures. You write it to the data asynchronously in the background. And then the stack is exactly the same. So all your applications work just the same, but there's no improvements there as well. So as it makes a tabular data stream, which is your rows and your columns, sends it back to the client, looks just like regular SQL Server. So there's no difference to you how that works. Okay, so we've talked a little bit about the engine. So we're thinking, what do we do? Well, technically everything is different. Internals are different. How it does concurrency is different. They exist in the database. They look just alike. But internally, there's some very big differences. Tables and indexes are extremely coupled. I was going to say bizarrely coupled, so I wasn't reading the slide there, but they're very coupled, and it's very interesting how that works and how that gives you some amazingly good performance, but it's going to blow your mind a little bit when you see the differences in how things work. Multi-value concurrency control is where I don't delete. I'm sorry. If I go out to the data, start a transaction at timestamp X, I get to see how everything was on the database at timestamp X forever until I close that transaction. I'm swinging my hand on a vertical plane here, horizontal plane. I'm sorry. And everybody else just keeps stacking on changes until you finish, and everybody's done using that previous version. So what this means is you don't have this blocking of data being deleted, data being removed. Everything is going to be inserts. I got a picture of that in just a few seconds. So we're looking at our physical design. Almost everything in your code, in your implementation, is going to be affected. It's going to change. So we're going to talk about how these things are changing. First, we're going to talk about table creation, what's different in building a table, index creation, and these asterisks are telling me there's going to be changes in how this works, and it's certainly for the better. Altering a table structure, that one's fun. I enjoy that slide myself. Then we're going to talk about accessing the data using T-SQL, compiled code, hybrid. And hybrid means sometimes these structures don't work for what you're trying to do, and I'll give you a scenario of that. And I have the code for that, and like I said, you can download, and if you want to know more, you can always ask me and I'll explain the code if it doesn't make sense. And then this no locks, no latches, no waiting. What does that mean? What is that? How's that going to change how you deal with your code? So creating storage objects, tables, more or less. Syntax is exactly the same as it was with a few additional settings. You're going to determine what is my durability? You have schema only. Now this schema only means no transaction log. You turn the server off, the data goes away. So, or no, I'm sorry, not just no transaction log. This is no delta files at all either. Everything's in memory. There's no logging. There's no nothing. It's just like you had a structure in memory. You put data into it. It looks like a table. It's fantastic for stuff like ETL or any transient data. Right? You never have to worry about that latency of transaction logging like you do even with a temp table. Even with a temp variable, right? You have that cost. Or you have what's called schema and data. And this is the durability we've trusted for years and years, right? You know that you have your data is safe anytime once the commit's been done. And we also have another setting which kind of takes what I just said and makes it into sort of a lie. Currently, if you think about your table now, you do a commit. Once you commit, you have this, you know it's saved, right? If the server restarts, that data is there. Well, they've added this new setting, which can actually give you some tremendous performance, called delayed durability. And this actually works for on disk tables as well. And what this does is says, make my log writes asynchronous. So as soon as you commit the transaction, it will immediately give you back control. And you've said, okay, go write the log file asynchronously. If it fails, if you have to roll back, you lose that data. So if you have the opportunity, if you can trust that you can redo some of your transactions, this can be amazingly important for your performance. I use it on our ETL databases, our data warehouse, because we rebuild it. If something crashes, we're going to rerun ETL no matter what. So, and Aaron Bertrand had a great article on that, tell you everything about it. So you also have less to work with. You have an 80-60 byte row size. And in the current version, this is enforced at create time. This means you certainly can't have large object types. They don't allow CLR, they don't allow SQL variant, date time offset, and row version. The asterisk is there because certainly large objects are allowed in the upcoming version. You have to question though, how much stuff do you want to stuff into RAM? And if you put a varchar max column and you say, put this in RAM every time, maybe if it's just because it's 10,000 bytes, it might be a good idea. But okay, so you don't have check constraints. You can't put any kind of check constraint on the table, which, it's bothersome coming in 2016 based on what I've seen and has been published, admittedly. No foreign keys. Well, like I said earlier, some people don't believe in foreign keys to start with. I certainly, except in my data warehouse, hate a database that doesn't have foreign keys. That can be updated because, you end up with orphan data. You run a query on the child, you run a query on the parent. They don't match, right? And that's, as an ETL developer also, to kind of do the gambit of building the relational database and the dimensional database at times. I hate it when that happens because I'm sitting here trying to figure out what to do with that data. Should I throw it away? Should I do this? I'm also a big fan of BIML. If you've ever seen BIML for ETL, and it uses the foreign keys, and you can build things based on those relationships so that you don't end up with bad data in your data warehouse. You get limited unique constraints. You have one unique index per table. This is a big problem, and we'll talk. I have a couple examples why, but you got to think, what if you have an identity column? Is that going to be your unique constraint? What if you have a customer number? Was that the one you're going to use? What if you have this 5-part key? Is that going to be your only key? You're going to migrate that to all your other tables? To me, uniqueness is probably the most scary thing you have to deal with because you get duplicate data, you have to unduplicate. And figuring out which row is the one to unduplicate to can be a nightmare. You have to have a unique index or primary key. And something for everybody, there's memory optimized temporary tables. Kendra Little has a fantastic article on that. And that's just, I don't know if you've used, because I can't see any of you, nobody's nodding their head or anything. But if you've used any kind of the temp table, the table object types where you say create type table, you have to do that for the memory optimized types, and then you just say declare table of that type, and it gives you that index. Just like if you were going to pass it into a stored procedure or something. So it's different, but it's similar. So you have this data quality question. So what if you have two customers and they have the exact same name, exact same address, exact same everything, but you assign them with different customer numbers? Well, this is terrible, but it happens all the time because sometimes they'll say, is Frederick Smith? You want to automatically assume Fred and Frederick are the same person? Maybe not, right? So this is the kind of deduping that any good business who's doing mailings and interaction with customers is going to do, because they have to say, do I want to send 16 catalogs to this Fred Smith who lives at the same house? Probably not, right? So you want to think about that. But let's talk about what happens if you have bad data quality and you're managing the train tracks. I've given train A to train B access to the same tracks because I looked and there's nobody using it. So we both looked at the same time, right? You want to use some sort of locking mechanism that makes absolute sure that they can't get to this. And I can think of some cheesy ways you can make it happen. We'll talk about it in a few minutes. So data quality to me is always the big question. What happens if? And if you can't answer that question safely, you can't test it. You can slow motion test things and make one query do this in the transaction, make another query do this in transaction, see what happens, right? Because if you can make it happen in long times, these millisecond changes, it's really hard to test millisecond differences. In my testing using a testing tool, which I have a link to later, I would get duplications on a very small set running lots of inserts at the exact same time. And when you get to these situations, it doesn't matter if it could happen. If it's a 1 in a million chance, people could die. That's probably something you should think of. Or if it's going to take you like 3 hours to fix every time it breaks, another consideration. So say you have 10 columns, one is not allowed in memory table. So, think, is this table really an OLTP table? We'll talk about the scenarios at the end, but is this really something that can be done in an OLTP system? So if so, then consider a vertical partitioning. Maybe 1 out of every 10,000 customers gives us a big, long 45,000 character explanation of why we stink, along with their order, of course, because they're buying something. Then don't stink this time. So that you could vertically partition and get away with that. You can join those two tables together when using them and still get some benefits out of the in-mem for the 99% of the cases if there's not a data there. Again, 2016 allows these, but consider how much can you put in there? Consider, and we do have check constraints. We've been told, it's been said. So you can say, maybe this is just because there's a 10,000 byte. You can say sometimes it's up to 10,000, put a check constraint, say length must be less than 10,000 or something. Okay. So when we're creating indexes, the syntax is in line with create table. The thing that's really wild about these is indexes are linked directly to the table. So you get 8 indexes per table, no more than that whatsoever. One of those has to be to a unique index. Never persisted, but rebuild on insert. I think I've said that again, but those 8 indexes can be a limiting factor depending on your need. But got to keep in mind when you're doing really OLTP systems, what should you be not doing? Should not be searching around and going scan every row, look for things. We're trying to get data in quickly. Build a data warehouse if you need to do a lot of querying out of it. So, okay, back in one of the more painful parts and what changed some of my design was string indexes must be a binary collation in the index. So that means all of your comparisons with that index to use that index, have to be a binary collation. So how would you do that, right? If you wanted to index something not binary, you would have to like strip out, you'd have to uppercase everything, take all of the funny characters, that's the American in me talking, you know, the ones with the little slashes on top, so the umlauts of the, you know, all those different characters, and change them down to like a non, to one of the base characters, so you could do any kind of searching. So then you've doubled the amount of space in your table just to be able to search it. So we want to limit it to things like customer numbers. So a customer number, even if it has data in there, is almost certainly going to be formatted a certain way. We don't let, you know, little c on the front of customer sometimes, big C on the, we don't do that, right? If you do, you probably shouldn't, for sure. Can I index a nullable column? That's, thank goodness, changing as well. That was kind of troublesome. Okay, so we have two types of indexes that we can work with. One is called a hash index. Now this hash index lets you do single point lookups very well. So you choose the number of buckets for your table, approximately 1 to 2 times the number of unique values. Even if it's a unique index, you need to have twice as many hash buckets. And once you, there's DMVs that you can check, and there's probably in that link there as well, that you can see how many, the average bucket length, you can look at the buckets. But you're going to find that even on a unique index, you're going to have 1 or 2, maybe 3 things in the same bucket. And if you have bad luck, you know, your hash indexes are generally a randomy sort of thing. You may end up with a bunch of things hashing to the same value. It just depends. And the more buckets you have, the more unique your values are likely to be because of the algorithm. So they're fantastic for single row lookups. If you have to do range scans, we're going to get out what's called a BW tree. So it's an excuse me. It's a B tree that's been altered to work with multi-value concurrency control. And the BW stands for, we're told, the buzzword tree, which I thought was pretty cool. So let's look at a bit of how the physical structures go. So the basic data for the row is you have the header, you have the payload. Simple, you know, that's very standard stuff. So the record header is we have a begin timestamp and an end timestamp. So when you first start the server, or when you first start whatever, this would be 0, and this would be infinity. So that row is that record version is the version. As time passes, you then may have multiple copies of the same row in here. This one's from 0 to 100. This is from 100 to 200. This is from 200 to 300, because people have made changes to it. And I'll show how that works in just a second. You have a statement ID, which lets them say, oh, I did this statement. I don't have to make another version because I'm in the same context. How many indexes do I have? And then you have the pointers to the next person in the next row in the index chain. So let's take a look at the structure here. So I've got the identity column here. The identity column, 1, we're going to say hashes to 3, 4, 3 hashes to 4, and 2 hashes to 6. You know, there's no sense to why that happened, but it does happen that way. Just you can't see the buckets. In country, we have countries USA. So we have 2 versions of USA. So this guy's row and this guy's row. So you go in here to the first row in the chain, and you follow the pointers down through the table. So right now, these rows are for all time. So let's say someone, again, I'm sure might be an international audience, but you know, someone moves away from my country into Canada. Well, what happens now is the identity column stays the same, right? But now we have 2 rows with the same identity value in there. So why is that? Because this version of the row is good from 0 to 100. This is from 100 to infinity. So when you're doing your query, it comes in here. I want to see 1, or I want to see 2. It's going to get 2 rows, 2 records from the data, and it's going to pull out the 1 row of data that it wants based on the timestamp. So it'll take this guy when it's that time. So the country, you'll see, we still have 2 rows that say USA, 2 rows that say Canada. So if we're looking for USA rows and we're anytime between 0 and 100, we're going to fetch these 2 rows. If it's later than 100, we're going to get 1 row. We're going to come down here. We're going to toss this out. And then Canada, we're going to see 2. At 50, we'll get the 2 rows. We'll toss this I mean, at 150, we'll toss this row out. Okay, hopefully that makes sense. It's very, very, very simplified, but that's kind of how everything works internally to give you this multi-value, this concurrency, so that you don't have to do any delete. See, if you delete the row, I don't have an example of that, we would just set the time it was deleted here, and now from 0 to 100 here, 1 to 200's here. After 200, the row's gone. So over time, there's a cleanup engine that goes and gets rid of these old versions, so you don't end up with lots of memory. So one of the reasons why the suggested amount of RAM is twice as much as you have data for, right? Because the goal is to be making lots of quick changes, and the goal is to throw those versions out, but you're going to end up with several versions. The fact that you do this way, so if you're in a transaction, okay, this guy's update wouldn't have been done, but you're only going to get one pointer here in the chain. So you'll see in a minute how this affects how we're going to deal with code, and it makes it super fast. And one of the things it does, it also makes it fail. You get some failures super fast, so you can decide what to do. The BW tree is slightly different than a current B tree, but it's really, really simple. So you have this page mapping table. So these are the pages that tell you where it is in RAM. You go to page 0 and you have C, R, Z. Unlike a regular B tree, you go to the left of the value, but from C up, so C to A is over here, R to C is in here, and Z to S is in here. And you have these pointers. So I want to see everybody who's a B. I come into C, I go B. Now these structures are timeless, right? You can have values that don't exist in the table anymore. But when we get down here, because there will just be no pointers. So now this pointer from B goes here, and we again have the same kind of chain to walk down and see the different rows at the different times. So I hope that's clear, or at least clear enough to give you an idea of what's going on. If you want to know more about the internals, and really you probably should, Caitlin Delaney's white paper she wrote for the last version was fantastic. There's a couple of papers that were, presenting academic sort of papers on the topic, which are really quite interesting as well. Books Online does a decent job of explaining it. There's a Tech Days presentation that I used earlier as a little bit of a reference. Caitlin Delaney wrote an ebook if you want even more, and it's a couple hundred pages for Redgate. And then I pulled a lot of the information about the OLTP enhancements from Aaron Bertrand's enhancements, not enhancements. Point that out for you. It's being recorded. Don't forget. Somebody's going to see that and laugh about it someday, hopefully me. Okay, so if there's no questions, I see no one raising their hand. That's good.
Well, we did have one question come in, and it was just, could you briefly go over the why of no foreign keys?
I will go over that, and I'll show you the difficulties probably why they didn't get that implemented in the first version, as I'll talk about how I tried to implement my own and all the problems that come with that. So yeah, I'll get to that. So now you've realized, your hash buckets aren't enough. You've realized that your column needs to be altered, the size. You want to allow nulls or take away nulls. What do? Well, this one's tough, but it's an easy slide to write. You just can't do it. Everything is drop and recreate. So you have to drop the table, recreate it, put the data back in. Don't follow that as a strict ordering because, drop the table after you put the data in the new table. But you can't rename the table. So, I mean, it's everything, nothing. You can't. You want to add a column, drop and recreate. You want to add an index, drop and recreate. Rebuild the index. Sorry, no dice. So it's a little bit tough. It's a very new product, so you want to get the design right, and when you need to make changes, there's going to be a little bit of a trouble there. So let's look at what you have to do. So if you want to allow your database to have in mem, basically all you have to do in 2014 Enterprise Edition is add a file group. That's a file stream file group, and say, in this directory, put the memory optimized data. And that's it. Now you're able to use this feature. that directory will grow fairly large. It keeps the copies, and it's cleaned up much like I said the internal structures are. So I want to create a table. So I have my schema, everything's the same. So what's different? So if I'm building an index later, or I'm going to do some comparison in native code, little tip to what's coming in a few seconds, well, I have to make it a binary column. So I'm making a bin2 binary column. Painful right there. Table's durable. I have to go to durability setting. I have hash indexes, so I'm going to say constraint primary key, non-clustered hash on the column with the bucket count. And we're estimating in this table we're going to have 25,000 rows or so. If we grow to 550,000 or 100,000, you know, those hash buckets get less and less performing. They don't perform very well after you have, if you have hundreds of thousands of rows or tens of thousands, or even, you know, the fewer rows you have in a hash bucket, the better it's going to perform. And then you have to tell it memory optimize equals on. So very simple stuff. One thing, in addition, you can also add indexes inline now in 2014 and up. So if you want to create your table, just like you can put primary keys in this structure, you can go ahead and put indexes in there as well. So you don't have to have this alter table, alter table, alter table. Okay, so that's kind of the basics there. So most typical interpreted SQL will work without any change. There's, you know, if you're doing updates in a transaction, it has to be. If you're doing a query, if you're doing a query in a transaction, you may have to add an isolation hint and tell it which isolation level. We'll talk about those in a second. Few exceptions that killed me. Why can't I truncate table? Because, you know, truncate table basically just resets the structure. That one kind of got to me when I was building some ETL. Because sometimes I was using temporary, using on disk. Sometimes I wasn't. Using on disk is much better to truncate if you want to reset your scenario. Merge can't be the target of a merge. Sorry, the in-mem table can't be the target of the merge. Probably the most difficult is you can't do cross database transactions. So I can't say insert into memory table, select from another database, because that forms a transaction. So you have to do, like, pass it to TempDB first and then do that. I mean, the fact that you can do it in TempDB is pretty fantastic, but there's no locking hints because there's no locking. We'll talk about that in just 1 second. So, you know, it's really simple. You can just write queries, joins work. There's very few limitations in using them. You don't get the benefit, though, unless you really start using compiled code. So this is compiled to machine code with a very, very limited syntax. When you look at if you look at the sheet here, you'll see they've listed what you can do, not what you can't do. And I've got an example of kind of the setup of these things. But it's just like a regular stored procedure. You have a create procedure, you give it a few bit of information, you start, you end, you put SQL code in there. Then you have limitations. Well, you can use substring, but you can't use left and right. Left and right, I mean, you can do left using substring. Right, of course, I was trying to build a customer number, and I wanted to take, you know, wanted to left pad data. Can't left pad the data unless you reverse it, which you can do, and then do the substring and then re-reverse it, which was much, much more painful. No subqueries, like even in an if statement, you can't say if row exists in table, then do this. You can say if 1 equals 2, and I'll show you how I got around subqueries in a few minutes. You can't use or, not, or in the where clause. You can't say where state equals Mexico or state equals Tennessee. Mexico? New Mexico, sorry. State equals New Mexico. That was not a Freudian slip whatsoever. You can't do that, right? You'd have to write 2 statements and maybe insert it into a temp table. Can't use on-disk objects. Can't reach out from this compiled code to get to your basic code. All string comparisons must be a binary collation. Thankfully, they're certainly going to change this. I know I saw or and in his blog, Aaron's blog, and I also saw this is going away, which that was what really made this tool much harder to use. So you can write some interesting code, and interesting is in quotes for a reason because it's really crazy at times. So how do we do it? We have this normal looking stored procedure with a few alterations. One, we tell it this is going to be natively compiled. We are giving it schema binding, so you can't change any of the objects that are this particular object owns. There's no ownership chaining. You tell it the owner that executes as, and it has access to anything they have access to, which is not as big a deal when all you can access is in-memory objects. But as things change, you want to really watch your use of execute as owner. Procedures are atomic transactions. So when you start doing some changes in the structures, you're going to want to error handle. If you don't want to stop based on some failure, you don't want to roll back, you can't do it without this. And that's kind of ties back to how everything works. And in a second, you'll see how everything works with the isolation levels. So it's a really interesting stuff you have to do. And then you just put regular SQL code. Anything that these procedures allow, you can. And when you compile it, it compiles it to a DLL that looks like a DLL, and SQL Server runs with it just fantastically. So sometimes you're going to find the handcuffs that you have from the compiled code is just too much. So we want to use some native code. So we want to split up our procedures, maybe have, in my cases, in my insert store procedure would have it took 3 stored procedures instead of 1. I would go out and I would grab a sequential value from a sequence in one stored procedure, return it back, format it like I wanted. I was trying to build customer numbers. So I wanted to take that, this is customer number 1. I wanted to add, C in front of it maybe, and a check digit, whatever I needed to do to format it such that was correct, and throw it in, put it in the table. Now I passed that to the store procedure instead of trying to format it. Originally I was using RAND because, again, we'll talk a bit more about concerns. There's a lot of chicken and egg problems in this presentation because you got to talk about one thing for the other. But when you're using snapshot isolation level or any of these based on snapshot isolation level, I can't go and see if anybody else has created a customer number yet. Have you created customer number 1? Well, I can't tell you because you can't see what I'm doing behind the wall. You can only see what your snapshot in time. So I did that outside, and I still get great performance, and I get kind of the code I actually wanted, rather than these random customer numbers that didn't fit my typical customer design. Okay, so no locks, no latches, no waiting. On-disk structures use locks and latches, the bane of our existence in performance, right? So we have this optimistic multi-value concurrency. We have 3 isolation levels: snapshot, repeatable read, and serializable. Now, what makes these different than the current versions is that they're done during the transaction, not before the transaction. So in snapshot isolation level, I'm allowed to see everybody's data as it was when I start my transaction. In repeatable read, I have the exact same thing, except at the end of my transaction, I'm saying data must not have changed, right? You cannot have, if any rows have changed, failure. Well, in a locking situation, what do? The person who's doing the repeatable read says, lock that data, nobody else can touch it while I'm doing it. So you go do your work, taking your time, you commit your transaction, everybody was waiting, moves on. Serializable says nobody could create data. So we have these isolation levels. So they're evaluated before or when the transaction's happening. This can make data integrity checking interesting. Go back to the foreign keys. And the essential difference is you really need to handle errors. I know a lot of people write code that just doesn't handle errors, and the only errors your application ever sees is a timeout because it's just waiting a couple of days, or a deadlock or something, and then it explodes. This is going to make life more likely to have these errors. So as an example, I have 2 connections. I want to update all the rows in a million rows. What happens in under any isolation level? What happens in on disk, right? Well, one guy starts and one guy right behind it says, okay, I'm going to wait, and you go ahead and update all the rows, and then it comes along and it updates all the rows again, possibly overriding the work of the next person. So one of these connections has just done 6 billion things and it didn't have to do, and the next connection has to do the same thing over. Well, in memory, what happens is if you've changed a row that another connection wants, the second it sees that you are still working on it, it says you can't do it. Hold on, wait till he's finished. Wait till he's finished. Wait till he's finished. So you can keep trying and trying. It's going to say no. So that makes concurrency stuff interesting. So as soon as he commits, you then can go check to make sure and see if things have changed using basic optimistic locking mechanisms, right? See if anything's changed in the row, see if a timestamp's changed, something like that. Now this is even if it never commits. If they roll back, their changes will be thrown away, but now you can make changes. If you think back to the structures and the way the time concurrencies are, they would only want one of these changes in process at a time. Now, so let's go to the next scenario. What if one connection wants to read all the rows and one connection wants to write all the rows? On disk, same thing, right? I'm going to select all the rows. I'm locking things. Guy wants to do the update. He gets stuck waiting for me to finish. Or if it happens to start at a different part of the table, we both get into this deadlock situation. Deadlocks are of that sort are probably a thing of the past for the most part based on update lock usage, but it still could happen. In memory, something interesting happens. If you're the reader and you're in snapshot isolation level, you always succeed, fine. But if you're in repeatable read, you can, both transactions do their business. This connection grabs all the rows. The other connection, I'm doing vertical hashes right now with my hands. They both end up finishing. If the writer commits before the reader, you get a failure. If the reader commits before the writer, it succeeds. So it's based on timing largely. Okay. So let's I'm running out of time. If I can have a few minutes over, I can cover this. So the difficulty of data integrity. So these constraints, we don't have constraints. So uniqueness on more than one column, what's the problem here? I want to go out and see if somebody else has changed the row. Well, I can't see their changes until they commit them, but I'm still back in the transaction when I started. So doing uniqueness, not really easy. Foreign key type checks, can't do them because what happens? If I do it in snapshot isolation level, I get the same uniqueness issue. If I'm in a higher transaction level, I can do a check to the table, but if someone has changed that row since I looked, then it fails. It says, no, that row's been changed. It doesn't say that that row's, the column I want has changed. The whole entire row is changed. So that, is a big problem. Check constraint stuff that can actually be done in the UI, client layer fairly easily. Check constraints, are trouble. So I started getting into this. I'm going to go through this really quick, but I tried using an index view for uniqueness. That was fun. I considered using multiple tables, and so now I have a unique constraint here and a unique constraint here, but I have no foreign keys, and I have no way to say two customers don't get the same row as well, and that really seemed like a mess. So what I ended up doing was just check and see if that customer ID, that email address is already in the table, and if so, return the value and use it. This stops so much of the duplication. You're down to just coincidences. And in a test application, coincidences happen, but in reality, they happen very seldom, and you just write checks to check this stuff. This is optimistic concurrency control. Okay, and then you're having to redo this stuff and not using the structures built in. It does kind of reduce the value of in-memory. So just to very briefly, high data insertion rates, read performance, because it's in memory, you get really fast read performance. Business logic, if you have this really intense business logic that you can force into their the stored procedures using the code that they have allowed so far, you're going to get that benefit of it being a DLL. Low latency, obviously you don't have to there's never any chance of reading the data. One easy use case though is session state management. So we might use a non-durable table for our session state management because we can just throw that data out at the end, right? If they lose connection, it's not going to be of value anyways. If our server crashes, we're going to lose their connection, and by the time they come back up, they're going to need a new session state. So there's that. Now I would say here, just don't think of this as a way to fix bad code. Think of this as a way to make an application that runs super fast and builds on on your needs, because you have that problem where multivariate concurrency control will give you, I really hate that word because I keep saying it over and over. So I did some tests. If you want to see what my caveats for you are, you can pause this when you watch it, the 15th time and know you'll be watching it, looking for all the Easter eggs I threw in. But I made this model. I initially put customer address out there in the database, but then I said, customer address, because your address line 1, address line 2, city, all those, I didn't want to force them to be formatted in all uppercases like this was 1987, right? I want people to be able to have formatted data and search for it the way they want, so I took that out. And I got some really good results. Using Atom Mechanics SQL Query Stress Tool, which is a fantastic tool if you have to do some stress testing. My first test with those tables with foreign key and instead of triggers to set the row last modified time, it was taking 0.0472 seconds. This is on my laptop. It's got an i7, 8 gigabytes of RAM, and an SSD. And you'll notice when you do your testing, if you're doing something with an SSD, you're going to get a lot better performance out of on disk than if you don't have an SSD, and if you have enough RAM to stick all the data in there. When I took those off, when I took the triggers off, I was down to 271 seconds per row. I then changed the tables to in-memory. I'm down a little bit more. When I used native code, and I changed everything into straight native code using the random customer numbers, I was down to 0.05 seconds per row. I turned off transaction log and I was down to 0.003 seconds per row. And you'll see I basically got an extra, 30 seconds out of that. So you're trying to pump in lots of data and you can fit the scenario probably better than even my test will. You can get even better performance. In memory tables, except for the customer address, and I'd use the hybrid method, I'm now down to 1.63 seconds. So I'm better by far than just taking off the constraints. I still have lost my constraints. I'm still doing limited checking. So then just don't forget the overhead. There's a lot of overhead in the different layers of stuff. If you look at, his tool has the overhead of capturing the performance data and putting it into a table on the side. And you have the TDS, all that overhead. Other people running, Xbox games on your computer at the same time. So we're back. I have to get back to work in the next little while, but I will certainly take any questions if anybody has. Hopefully I answered that foreign key question well enough. If not, you can all go back to work as well.
Hey, thanks for doing that for us. The only really question I had was the primary keys have to be GUIDs. He says, is that right? Like, really? Is that right?
No, the primary key can be anything.
Okay.
Anything that's indexable. They can be GUIDs. I used all integers. You could use the natural key as long as it's a binary value. So if you want to use the customer number to make that your primary key and use that for all your references, you could certainly do that.
Okay.
You just get one of them. That's the big limitation.
That's all the questions that I have. Several people saying thank you very much. It was an excellent presentation. And thank you for taking the time to do this for us. We really appreciate it.
No worries.
Great. Thank you everyone for joining this month, and we'll see you for the Palooza. Keep an eye out on our website, and we'll see you for that next month. Thanks, everyone.
I'm waving by. Just can't see it.